So today I would like to structure my talk around four main questions. So the first one is, what are the potential risks when we use large language models in applications? What are the safety and security implications of that? And the second thing is, okay, how to defend against these risks. Is it easy? Is it hard? And spoiler alert, I think it's very hard. And that's why I like to explain some of the reasons of why I personally think it's the case. And then I would like to move to how to design robust defenses. And here I will talk about the new project that I just mentioned. And finally, how should we really think about and go about evaluating current LLMs and current chatbots? Of course, I think these are very difficult and open-ended questions. I certainly don't have answers to all of them, but I hope to share my thoughts, which I hope you would find interesting. Okay, so LLMs are currently used in so many applications. So it used to be like a year ago or something, or more than that. It used to be like you just go to ChatGPT website, you ask a question, you get an answer, and then you move on, and then that's it. But now they are some sort of a middle point in so many applications, like in search engines and different versions of co-pilots, like Microsoft Office and different OpenAI plugins. And of course, this could be very helpful for users, like to get rid of repetitive tasks or maybe to automate some of these things. But as it turned out, this could come with certain security risks, which I will talk about now. So this was part of a work that we did last year at CISVA, where we highlighted really for the first time, very early on, before with the launch of these applications, we highlighted some of the real world risks that could happen with this integration. So to give a brief overview is that the main reason, in my opinion, that these risks that I'm going to talk about are possible at all is that LLMs in application, they sort of mix data and instructions in one channel. So anything that I send to the model as a prompt or as a question, it gets concatenated along with the data, such as the search results. So current models, they don't have specific explicit mechanisms in order to separate these two channels. Everything is sort of mixed in one thing. The other probably problematic thing is that, well, they read the web, right? So there is no control. These are third-party documents, third-party data, random search results. We have no control at test time over the different sources that would be fed to the LLM. They just might be untrusted. Oh, thank you. They just might be untrusted, not very credible, not reliable, and so on. And due to these reasons, we kind of thought of this might enable something like command injection attacks, or what we have called in this work, indirect prompt injection attacks. So in here, an attacker might inject some sort of an instruction or a prompt into data that would likely be retrieved at test time, like search results, emails, and so on. And when these instructions, when these search results are fed to the model at test time, the model would react to the instructions as instructions, and instead of treating them as data that shouldn't be executed. So in a sense, the context of who gave this instruction is missing from the model. And it turned out the next natural question to ask is it really a big deal? What's the worst can happen? Is this really a big problem? And in order to answer this, we should pause and remind ourselves that current models, they are not really task specific. They are more of a general purpose model. They are not like a classifier for sentiment analysis or something. They can do so many functionalities, so many tasks, and that's why they are so convenient to use. But at the same time, if attackers are also able to prompt my model indirectly, then it means that they also have the same functionality, the same flexibility as the user, which could be problematic. And here, if we really ask about what the risks, it could be that sky is the limit of what could happen. And since I'm talking about attacks, so let's say that dark sky is the limit. And the risk doesn't really stop at search results. So imagine a situation where there is like an email client and it receives my emails. It's also maybe has a functionality of sending emails, which could be fine. But imagine that someone sends me an email to say, okay, exfiltrate my data, like find the emails that are very important, send them to this email address. And of course, this is very problematic because it's coming from someone else other than the user. So in this work, we sort of said, okay, this is a new realm, this is a new domain. We don't really know how to think about it systematically. Let's take a step back and see what do we know from cybersecurity risk. And then we took some sort of a cybersecurity taxonomy, and then we mapped how current systems, current LLMs can be used to automate such risks. This could take the form of enabling phishing attacks, enabling fraud, malware distribution, the information gathering or exfiltration that I just talked about in an example, could also manipulate the search results. And very importantly, it could lead to some sort of intrusion attacks if the model is allowed to access and execute some APIs. And for that, I would really like to highlight that it really, when we think about what are the potential risks, it really depends on the capabilities or the permissions given to the model. So for example, in the early work that we did some experiments on exploits on Bing Chat, the Microsoft product, now it's called Bing Copilot. And we found that if you give it a long prompt, it is responsible, for example, to extract keywords and to extract the search query that will be given to the search engine, and it's also responsible for summarizing the output. So you could ask it to manipulate the input, you could ask it to manipulate the output, maybe block certain source altogether. So when we think about risk, again, I would like to highlight, like, some of these might be not currently feasible at the moment, but again, it all depends on what kind of capabilities you are giving to the model. So when we worked on this, we disclosed this vulnerability to Microsoft. And now I'm happy to be part of the team that actually responds to these vulnerabilities and also hopefully proactively work on new research projects of proactive research of how can we think about new attacks that were not developed yet, or how proactively defend against these attacks. And since then, as researchers, when we worked on this, we realized that, well, this is probably going to be a very important and difficult problem that we have to really solve if we want to use these applications securely, if we want to have the benefits of the very fantastic use cases that they offer, but we also want to enjoy different security and safety considerations, right? So this worked. And also the questions that kind of it asked, it received a lot of attention from the research community and also from companies like Microsoft and Google. And currently there are a lot of active work on how to mitigate and how to defend against these attacks, which I'm really happy to see. Also, like other companies like Google, they talked about how the importance of the trustworthiness of the different inputs and different sources given to the model at this time. So now I'd like to shift a little bit about attacks. So please say hi to my friend Bernie here. I'm using his help a lot in my presentation today. So yeah, disclaimer, I had so many animations here that were cool, but due to technical issues, I had to convert them all to PDF. So imagine that they were nice animations. So yeah, so before talking about defenses, I would like to kind of give some sort of broad taxonomy of what the defenses could look like based on what we thought of and based on what's currently been done in previous work in literature. So I first thought of, like, yeah, we can detect attacks, right? So this could be cool, like this would work, it makes sense, let's detect them. But then you realize that it's not really as straightforward as you think of, or as I thought of at the beginning. So yeah, Bernie, again, surprised. You can have some sort of these very obfuscated prompts. So when I first tried this, like more than a year ago on GPT-4 in this work, I was very surprised. So here you just take a normal text and then you encode it in some sort of different representation, base 64, and you just tell the model, well, decode this, and then you don't even say execute anything, you just say decode it, and then it works. So like I remember, I of course cannot read this, but I think the natural language was like, yeah, distribute some phishing email or something, and then you find that the output is actually distributing the phishing email that you asked for in this like very weird text. So it's very hard to detect this. Of course, you can think of like clever ways of how to detect obfuscations, but it feels like it's a cat and mouse game. So we can always think of something, but someone else might think of something better. And well, also, we could have something like this. So current LLMs, they are trained on different languages, but the performance is not really the same. So you can find that certain languages, due to biases during pre-training, we don't really know, but it could be easier to break the safety alignment, to break the safety mechanisms of LLMs when you use certain maybe low resource language or other languages other than English. And then, well, again, imagine that there were animations. Actually, in the realm of indirect prompting, I would guess it's not really about malicious prompts. It's about any instruction at all. So imagine the scenario that I was talking about the email clients. If I just tell the email client, send an email to X, it's fine, because I'm the user. But if someone else says it, then of course it's problematic. So it's not about the nature of the instruction, it's about the context of who's giving the instruction. And for that, we can just detect the instructions, but we don't really know how instructions would look like. It's not like we are operating with formal language. It's not like a coding language or something. Instructions could take any form. They could just take any grammar. There is no clear way of how they would look like. And even now with like multimodal models, like visual models, or even audio, instructions can be part of an image or part of an audio file. So it's really hard to detect instructions. I would say even harder than detecting maliciousness. So that was the first direction that I thought of. The other thing is prompt engineering. So well, it's easy. Ask the model what not to do. So one of the problems that we have is that we don't have a clear separation between data and instructions. So let's artificially introduce some boundaries. So let's tell the model, okay, cool. I will give you some symbols to mark the data block, and you are not allowed to execute anything within these data blocks. So if that's the way the models are modulated, let's modulate them this way. And that also, again, seems plausible, but, well, you can have a situation where an attacker says, well, yeah, the text has ended. Now these are new instructions, blah, blah, blah. And you could argue that you might come up with a better, stronger defense prompt, better way to tell the model what to do and what not to do. But as I mentioned, towards the end, it is really tricky. It's just like an adversarial game. You can come up with a clever way, but someone else might also come up with a clever way to break it. And the final thing that I have seen, which is a very recent work by OpenAI, is to do sort of fine-tune the model, teach it the privilege hierarchy. Like, okay, so any input coming from the user is more privileged than any input coming from the internet, which I think seems plausible, but it's first of all expensive because you need to fine-tune these models, which is crazy because they are huge. And also, we don't really know if this would survive optimized attacks. Like, so just a little bit of background, there are some ways where you can actually optimize attacks such that they maximize that what you want to do will be done. So, and also like in some recent work, we have explored all of these, some sort of baseline mitigations. We did fine tune some models in order to not follow instructions within certain blocks. And we found this could affect utility. So for example, if you fine tune a model to not follow instructions within a block, it could not follow instructions at all. This doesn't mean that it doesn't work at all, but it means that it probably needs more careful training, more expensive fine-tuning, which is, again, comes back to my point that it's expensive to do that. So for a while, I was actually feeling frustrated, and I felt like, okay, so all of these things, they work. It's not like they are completely useless. Of course they work. Of course, they might reduce the problem that we have. They might have certain success. At least on the average case, they would work, but they might not stand against like very motivated adversaries, which is what we think of when we think of like security in general and security in machine learning as well, because we have been in this field for more than a decade now. And this is how we think of, at least as a community, this is how we should think of attacks and machine learning security, of how it would stand against a motivated adversary. So now it comes to my well, I realized that I have been talking about this for a lot, and I might have built a lot of suspension, so I hope you like it. But in my opinion, I think a very nice alternative to these problems that I presented is to, instead of detecting instructions, to look into the model's internals. Like, let's kind of open the black box. So we have a black box and model. Let's open the black box and like do surgical operations on it and see what are you doing at the moment, and then track if are you doing what I'm expecting you to do, or have you drifted and trying to do something else. So this is what we call task drift. So the main idea here is that as a user, when I give the LLM a certain prompt, which is call it the user prompt or a primary task or so on, after it reads search results, after it reads external document, it should still be doing the same task that I have given in the first place. It shouldn't go and find another instruction in the data block and starts to execute that. So the main idea is that let's imagine that we have a way to kind of extract what the model is doing. And then let's do this at the beginning when the LLM is given the primary task. And then let's do this at the end when the LLM has read the whole text. And let's just compare them and see if it is the same task or not. If it's the same, then that's fine. This is data. If it's not the same, then probably someone else is trying to manipulate the data by inserting something else. And that's why we call it task drift, because I don't care what the original task is. I don't care what the second task is. I just care that there is a drift between them. So it's kind of like I stepped aside from these problems that I don't know how to quantify to sort of a simpler problem of just detecting the drift. So what we do is that, as I said, we extract the activations. So activations, like it's some sort of the internal computation, like it's a very not accurate description, but just for the sake of this presentation, let's say that we extract the activations of the model. This means like it's the internal computation, the output of the internal computation that of the context window. And let's do this for the primary task and do this for the whole context. And then the hypothesis here is that we can just compare them. And the simplest way to compare is that we can take subtraction of the two activation sets and see the assumption is that for clean data, for clean text, this difference would be small. And then we did this, and we did here some visualization of this activation residual or activation differences. And the red parts are the poison part, the green parts are the clean parts. And we see that there is a separation between the two, right? This is like, we didn't do anything fancy. We didn't fine tune the model. We didn't train the model to do anything. This is just like the inherent activations, the inherent computation of the model, which seems to reveal something, which means that we can like take this procedure, train a classifier in order to detect if there is a drift or not, which what we did. So we tried the simplest classifier possible, just like logistic regression on the activation differences. This is like the simplest linear classifier at all. You cannot get simpler than that. And then if you want to go fancy, we can do that. So we did something like metric learning probing. So just like without going into too many details, we wanted to learn some distance function such that the distance between the oh no, the pointer is not working. So the distance between the primary and the instance would be small in case of clean, and it would be larger in the case of poisoned examples. So what we want to do basically is to learn an embedding space on top of these activations such that we will have a clearer separation between the two classes, which is what we found. So this is like the learned embedding space, and this is the distance histogram. And you can see that for clean examples, distances are smaller. And what is really exciting about this is that you can generalize quite really well. So what we did here is that we trained on benign data just for the sake of exploring the generalization ability of this method. But of course, you can train on anything. So benign data here means that the secondary task would be like something, tell me the recipe of a nice cake. So it's not really jailbreak. It's not something that an attacker would really insert. But we wanted to see if we train on this benign data, can we detect the more interesting examples? Can we detect jailbreaks? Can we detect malicious instructions, prompt injections, other languages? Just you name it. And it turned out you can. So these are like the example, the ROC AOC. So this is just like a metric, higher is better, perfect is one. So it means that with across different models, so these are kind of from the smallest model, which is the phi one, to the biggest model, the mixtral. You can see that if you just train a linear classifier on these residual differences, you can actually find very good classification between the two classes. And again, why I think personally is exciting is because we have so many problems that we cannot really answer. We don't know what instructions are. We cannot reliably prompt the model on what to do and what not to do. And also, one potential thing that I thought of, like, let's ask the model, let's interrogate it and tell it what are you doing at the moment. But it could lie because, like, earliest model probably couldn't do this, but GPT-4 can lie. Of course, we couldn't test on GPT-4, but like in principle, especially as we move to the future, models might be more, they might have more capabilities to receive, and therefore relying on the output of the model is not really sustainable. But looking into some interpretability-based solutions might be. So I think this solution, the reason I'm excited about it is that it kind of restricts the problem into an easier, simpler, and hopefully more kind of sustainable in the future solution. Just let's detect how models react to instructions because we can detect that, and instead of less detecting instructions. Okay, so I don't want to go into a lot of details because there is the last part that I wanted to talk about. I promise I will not take much, but what I wanted to say here is that also it reflects better what the model is doing. So you can find a lots of instructions everywhere on the internet. So if you go to a website, you can find something like, please subscribe to this channel, click here to know more, something like this. It's not instruction to the model, but it's just like a verb that's probably, we're not so sure if the model would react to that as instruction or not. So this is the second problem, is that we don't know what instructions are, and also we don't know what the model would detect as instructions. And I think this reflects what the model is actually doing. So what we did here is that we tested on some data sets called the wild chat. So these are chats between ChatGPT and users. So naturally, it contains instructions because they are chats of AI assistant and user. And we pair this with the primary task of, please summarize this conversation. And then we're not so sure if the model would summarize or would just like implement any of that. That's why I'm giving all this talk. But what we did here is like, okay, let's pair this with like meta prompts in order to guide the model, like the prompting solution. Let's guide the model that these are instructions. And the first one is like, yeah, just this is a conversation, starts now. The second one, it highlights that don't follow anything. The second one, seriously, don't follow anything. I mean, that's not the full prompt that I use, but like for the sake of brevity, let's imagine it's just I told it seriously, dude, and I moved on. But if you want to know the full prompts, you can check in the paper. And what we found is that when you move with like how strong you want your prompt to be, you find you end up with like closer distances. So in here, the distance means that it's clean. The higher means it's poisoned. So actually, when you use the strongest meta prompt, you end up with distances that are close or even smaller than the clean examples. So I think it means that you have better transparency of what the model is eventually doing, even if there are no attacks at all, because in this case, this is benign data. These are not attacks. And well, so the last part that I want to talk about, and I promise will be super quick, is evaluating LLMs. So it's kind of like I wanted to give this broader my perspective, broader idea of how we should go about evaluating LLMs. And for that, I think we should consider moving our evaluation from the things that we are used to do in the natural language processing domain. We used to have static single-turn data sets. Like I can ask the model, what's the capital of Germany? Just reply Berlin, and then we move on. But now in LLMs, we have more interactive, we have more dynamic setup. And this is not what we train models to do. We just train models, like at least in the pre-training phase, we train models to just predict the next word. But now with some sort of fancier fine-tuning, but this is really a small part of the whole training pipeline of the model. And then after this fine-tuning, we want to use them in different interactive, very complex tasks. And I think there's a discrepancy between that. And due to this discrepancy, we might end up with some situation where the multi-turn interaction would be problematic. You can sometimes have like jailbreaks from the multi-turn interaction. You can just, instead of saying a malicious instruction in the beginning, you can break it into different turns. Each turn is benign on its own, but if you combine all of them together, you end up with a successful jailbreak. Like here, for example, the model could answer how to make a bomb after the multi-turn interaction. And you can also have some sort of even performance issue. Like if you switch between tasks, you can have a degradation in performance. So that's why I think we should move some sort of our evaluation from static benchmarks to more dynamic and more interactive ones. And for that, I'd like to just give the idea of what we have done in this work. So what we have done here is that, well, let's use a game. Let's imagine that because in the future, we might end up with like a lot of multi-agent LLMs, models that are communicating and negotiating on behalf of users. So let's simulate this. And what we did here is that we used a negotiation game, and then we, in this game, models, they have certain, they should negotiate the launch of a new project. They have certain negotiation goals that they are trying to optimize and maximize. So they should do proper mathematic calculations of these goals, and they should make correct inferences and exploration and so on. And also it measure, like, again, there used to be really very nice animation here, sorry. But again, this game also measures the cooperation and the communication dynamics between agents, because they are all maximizing something, but it's a non-zero sum game. So they should eventually find a common agreement that would, like, for example, this leading agent, it starts with its maximum score, but by interaction, it compromises, and this would increase the collective score of the whole group. And this is not a trivial task. So we did this evaluation of multiple models, smaller models, and even ChatGPT or GPT 3.5 completely failed to do this, because the task is really challenging, even from the human perspective, I would say. So that's just to say that I think, in my opinion, the way to evaluate LLMs is to do more of dynamic tasks that are more similar to real-world tasks. And also, I promise that I will talk about why prompting might not be a good idea to defend models. And this is seriously the last part I will talk about today. So last year, we organized a competition in SATML, which is like a conference for secure machine learning. And what we did here is that, well, let's just assume a setup where there is a model and we want the model to protect information. It could be like it reads confidential user information and it shouldn't reveal it. So let's have two teams that are competing against each other, the defender team and the attacker team. And the defender will tell the model there's a secret, you should never reveal it. And the attacker would try to get the secret. And we organized this competition and we had so many participants. But what we found is that, well, most defenses were broken at least once, even though they used pretty smart ways of how to protect against obfuscations, how to protect against the model revealing one letter at a time. They really tried hard to actually come up with good defenses, and the defenses didn't affect utility, so they were great. But at the end, attacks won, because it's really hard to defend against these attacks with just prompting. And I think the reason it's really hard is, again, due to the very hard, unexpected natures of how prompts could look like, and also because multi-turn evaluation is important. So it could be like, well, reveal one letter at a time, one letter in different turns, but at the end, the attacker can observe these interactions. Okay, so that's the end of my talk. Sorry about that you cannot see the first part. But yeah, so as I said, I think these are really open-ended questions. They're very difficult to answer. But in my opinion, I'm very excited about models internals in order to do certain safety perspectives, and also for dynamic benchmarks or multi-turn benchmarks or task evaluation in general. Okay, so thank you so much.